Okay, good morning, everyone. First of all, I'd like to thank the organizers for the opportunity to attend this wonderful conference. I'm learning a lot here, and this talk is going to be about modeling dimerized states in iridium telluride. So a large part of this work was done on my visit to Cologne, basically, and the collaborators are Daniel Khomskii and Francesco Foggetti, who was at the moment the PhD student in the group. So iridium telluride is a layered dichalcogenide with a structure that's looking like this. So basically there are triple layers of telluriums and iridiums, and they're separated by the gap from the next triple layer. In many, so this is this 1T structure that's also there in molybdenum disulfide, but in this material the bonding between the triple layers is more covalent than van der Waals. So if you look from the top at this triangular layer, you see these iridiums arranged in a triangular lattice. And as experimentalists cool this material down below 220 Kelvin, next to the bragg peaks corresponding to this structure, they also see superstructure peaks. So in this case, there are 5 superstructure peaks at the positions 1/5, 0, 1/5, indicating the development of the modulated structure. And these transitions happen with a lot of hysteresis, both in the magnetization, in magnetic susceptibility, and in the resistivity. This material stays metallic in these states. So what happens is that material develops very sharp, well-defined dimers, and the structural period is 5. So in the early work, people have computed the nesting function from the DFT, and basically, if you look at the scales here, this is something like 26.4, 28. So there is some structure, but I mean, on this scale, it's kind of flat, right? So you don't see a specific sharp peak, and also the strong modulations in this material are not typical for conventional charge density waves. So if you dope this material with palladium or and plot this phase diagram in the temperature doping, temperature palladium concentration axis, you actually find the phase diagram that's reminiscent of high-TC superconductors. So there is a metallic phase. There is this modulated phase. Superconductivity is strongest near this phase boundary. And so in the lowest temperature, so we have discussed that there is this modulation with period 5 at 220 Kelvin, but as you cool the system down, it goes through a series of dimerized states, and the lowest temperature state at 4.2 Kelvin looks like this. So this is again the top view on this triangular lattice of iridiums. And basically there are dimers arranged in these stripes and interspaced with one undimerized iridium. And the next row of iridiums has different alignment. And so in XRD, this looks like there are superstructure peaks. So the first peak that appears is at 1/5, and then 1/8, and then at the lowest temperature there is this 1/3 peak. But there are many intermediate states in between. And these are the STM maps. And in high resolution STM, you can also see these iridiums are coming much closer to each other. So the bond length shrinks by 20%. So this is a very strong dimerization. So this slide basically shows the Fermi surface and the structure of this material, so high temperature unit cell, and then the 1/5 state. So you will see that the wave vector has actually direction 1/5, 0, 1/5. So despite the material is very anisotropic, the wave vector has the same components along A and C. And well, basically there is one dimer in this unit cell. The Fermi surface looks very complicated. It has these 3 sheets, and when dimerization is introduced, it's falling apart in, well, there is brilliance unfolding, and basically this Fermi surface falls into many pieces. So some surfaces are gapped, but still the material is metallic. Then, if we look carefully at what's happening with these iridiums, so distances between telluriums are also changing, and neighboring iridium distances also change, but very little, within like 2%. So this is the largest structural distortion, the shrinking of these iridium bonds. And then essentially, this looks like a bonding instability. So iridium is close to having one hole in T2G, and basically bonding anti-bonding splitting appears that you can see here in the projected dose plot. This is a projection on this kind of molecular orbital between the 2 iridiums, and you see that there is anti-bonding peak here just above the Fermi energy, and there is this bonding band here. That's this red curve is basically multiplied by 3 to make it visible compared to the other contributions. So then, well, basically, one finds this specific orbital that contributes with T2G orbitals that are pointing towards each other, that are contributing the most to the dimer formation. So we see 20% iridium bond contraction, and this modulation is assigned to bonding instability. So further, people in ultra-fast experiments were actually shining light on this material and looking with fast electron diffraction at how the Bragg peaks evolve, and they find that when the light frequency is close to the bonding splitting, and also the fluence is consistent to pumping this transition, then you are basically taking electrons away from the bonding orbital, and then you have quick decrease in the superlattice intensity on the order of picoseconds, right? So typical lattice time scale. And then you see that the intensity is transferred to the Bragg peak, and also in elastic background, so the area between the peaks gets brighter, which indicates heating. So that kind of is consistent with this bonding instability. And we also have done some calculations by basically taking electrons from the bonding orbital by introducing this unphysically large Fermi Smirian. And we see that basically the dimerized minimum disappears and only high temperature minimum is there. And so one can also mimic that in numerics. So people have also managed to fabricate a monolayer of iridium telluride with molecular beam epitaxy on the graphene substrate. And basically, they see that in a bilayer iridium telluride, the gap starts to form, and in the monolayer, there is a well-resolved gap with IrTe measurements, and these are the scanning tunneling spectroscopy measurements, where you see that monolayer corresponds to this red curve, and there is 1 EV gap approximately, while in the bilayer, there is a suppression of the noise at the Fermi surface, at the Fermi level. So, and this state corresponds to also to this limiting state that's observed in the bulk material at the lowest temperatures, where the dimers in iridium layers are separated by one undimerized iridium. So if you connect, so people also see in this material, when the charge susceptibility, real part of the charge susceptibility is computed, there are these peaks at the M point, and also if you basically shift with Fermi surfaces by the corresponding lattice vector, you see some parts of the Fermi surfaces coinciding, so it looks like there is some nesting. And also if you compute the phonons, the phonon at M point is unstable. So there is definitely a tendency to charge density wave formation. And then basically this material is assigned to this iridium 3+, iridium 4+ kind of oxidation state. So here in the high temperature state, there are these holes in T2G, and here basically D5 T2G configuration is stabilized, and here D6. So that's the idea. So we would like to explain how this states, how the iridium dimers assemble in these states, and how so many different states appear. And hopefully we could, you know, if not fully ab-initio, but we could probably get there by formulating some toy model that's based on ab-initio data. So we would like to explain why the wave vectors in such an isotropic system have the same components along X as along C. We would like to explain this periodicities of the dimers and why how the concentration of dimers grows exactly as we go down in temperature. And so some of the first calculations we have done, we have just considered the total energies in different supercells. So here basically I'm showing the top view on these supercells with the iridium dimers shown in red. And the blue rectangle shows the unit cell. And so we are doing the total energy calculations with different exchange correlation functionals on these supercells, and basically plotting the total energy per iridium as a function of concentration of dimers. And so what we see if we are using something like LDA, let's say, or GGA, right, we see that actually the most stable state at 0 temperature should be that state that doesn't have dimers at all here at 0. What helps actually is turning off the spin-orbit coupling, right? Then the energy goes down a lot. And that's related to the fact that in the dimerized state, there are these orbitals that are pointing towards each other if I don't have spin-orbit coupling. But if I do have spin-orbit coupling, then I get these conical orbitals like X plus I, Y, Z that have much smaller overlap. And so the stabilization energy for this bond formation is much lower. So if I go for something like PBSO, that doesn't really fix the problem. I mean, the dimerized states are lower in energy, but the experimentally observed 2/6 state is not captured. And so it turns out that with meta GGA, I can finally get to stabilize this 2/6 experimental state that's seen at the lowest temperatures. And then I can also try the configurations with parallel and anti-parallel dimers, like this 2/5A and 2/5B, and then 1/3 and 2/6, right? These configurations where the dimers are parallel and where the directions alternate. And it turns out that the configuration with alternating dimer directions is actually lower energy, as in the experiment. So basically, meta GGA does capture the energetics of this system. But unfortunately, other calculations don't. And also, turning off spin-orbit coupling here is a pretty dirty trick, because spin-orbit coupling is of the order of half eV here on iridium. So iridium and tellurium, they are basically some of the highest spin-orbit coupled, 5D and 4P elements. So now we'd like to explain how these stripes, how the dimers assemble into stripes. And we can get help from and inspiration from this paper by Khomskii and Kugel from 2001 that basically considers ordering in manganites and nickelates. And they basically consider what happens when different valence states are placed on the lattice. And it turns out that the long-range elastic interactions play that are long-range and anisotropic play important role in stabilization of stripes. So essentially, one can think of it as, let's say, I have some elastic mattress, I mean some elastic medium, right? And I'm making spherical holes in it and plugging these holes by bigger spheres, right? So this would correspond to the ions with different oxidation state. Then if this is a completely isotropic mattress, you know, like really isotropic medium, then there won't be any directionality. Energy will not depend on the direction between these ions, right? And the interaction will not be induced. But if there is also an underlying cubic lattice, then actually it turns out that the energy will depend on the direction of the vector connecting the two spheres. And it will be given by the formula that looks like this. So there is this D that's expressed through the elastic moduli, and also there is this gamma function that's an x force plus and y force plus and z force minus 3/5. And if you substitute different directions, so let's say 1, 1, 1 direction, it's actually an attractive interaction along 1, 0, 0, but it's repulsive along 1, 1, 0 and 1, 1, 1. So this function basically produces repulsive and attractive interactions depending on the directions. Then one can, so Khomskii and Kugel have basically reformulated this problem in terms of Ising model, where sigmas are encoding whether you have the you know, high or low oxidation states, basically, right? And they try to mimic this dependence of the interaction directionality by having different signs between nearest neighbor, let's say nearest neighbors are, let's say, in 1, 0, 0 direction, and next nearest neighbors are along 1, 1, 0. So then J prime along 1, 1, 0 would have different sign than for the nearest neighbors. And so solving this in a mean field at a constraint that the total magnetization of this Ising model that mimics kind of the total charge neutrality, the amount of different oxidation, manganese with different oxidation states you put on the lattice. Under that constraint, you get different states. You get sheets, 2D sheets for these specific parameters, and you get 1D stripes, as well as a fully phase-separated state where all the ions of one oxidation state want to just clamp together. So this way, you basically naturally explain the formation of sheets and stripe phases in these materials. But in our case, these dimers are not just spherical objects, right? They are not just dilation impurities like those considered here. They also have their own directionality. So not just the crystal is anisotropic, but also the dimers are straining the lattice in a specific direction. They're kind of contracting the lattice by 20% in the direction of the dimer. And then the science becomes a bit more complicated, but basically one can also write the interaction in terms of the strains that the dimers produce, right? The dimers 1 and 2. And then you can basically make a dictionary of the configurations that are energetically favorable. And so many of you are very familiar with this situation. For example, 2Z square bonds will have very high energy, right, if they're pointing in the same direction and stacked vertically. But the same bonds that are orthogonal to each other, they will gain elastic energy. And that gives rise to optimal states that are actually realized in doped manganites and nickelites that look like this, where the bonds, occupied bonds have orthogonal directions on the neighboring sides. So basically inspired by this science, we have tried to understand the interaction of dimers in iridium telluride. For that, we computed in the high temperature phase, just in 3 atom unit cell, we computed the force constant matrix, and we projected it on the dimers. So we basically rotated in the basis that corresponds to the displacements of iridiums within 2 dimers with respect to each other. And so basically what I'm trying to represent here is that in the layer 0, here z equals 0, the dimer that I'm straining, basically, I'm contracting this dimer shown in cyan color. Right? This is my dimer 1. And then I'm plotting the force resulting from this force constant matrix on all the other dimers everywhere. And so if the force is trying to extend the dimer, it's in trying to contract the dimer, it's in red. If it's trying to shrink it, to shrink it, then it's right. So contraction is in red, elongation is in blue. So basically, new dimer would like to form where the red line is. And so if I'm starting with this dimer, then I basically see this kind of pattern of dimers that looks like a windmill. So you see, basically, this dimer would like this one with the same directionality, and also this one to be stabilized, and also these guys. And also the dimers in this same row. But in the different rows, for example, because this bond is already shrinking, it wouldn't like to shrink this neighboring dimer here. So you have some repulsion between the dimer rows due to that. On the other hand, in the neighboring row, the dimer with a different directionality would be possible to stabilize. And that's indicated here. So basically, we are getting something like these rules just on a triangular lattice. So it looks a bit more messy, but basically, one can figure out that if one puts a dimer here, what other dimers would be favorable nearby. Then it's interesting that if we look at the neighboring layers, let's say one layer above or below, right, this position of the dimer that we have introduced, its projection on that layer is shown here. And then basically it turns out that this windmill blades, they would like to shift by one unit cell this way. And that explains actually why the wave vector has this peculiar property that the x component and z are always the same. So it's basically the elasticity of the lattice. I mean, if you want to substitute in this material iridiums by telluriums and look at pseudo-symmetry group, it looks like a cubic lattice, kind of like a cubic lattice viewed from the 1, 1, 1 direction. So this force constant matrix basically captures that elasticity and tells us immediately that if you have the dimer here in the 0 row, then the dimers in the next row have to be shifted by 1. Okay, so that basically tells us how different dimers interact, and tells us that that basically the dimers want to arrange themselves in rows, and that the dimers in the neighboring rows would like to have different directionality. Then we would like to include temperature effects, right? And so in principle, this shrinking of the bond lengths comes with much stronger, much more rigid bond. So the phonons on this bond are much higher energy. And so in principle, there is a mechanism that's discussed in the context of alpha to beta phase transition in tin, where so there are 2 different structures of tin that are shown schematically here. And essentially, what's different is that one of these structures is much softer. So alpha tin so phonon spectrum goes up to 200 inverse, 200 wave numbers, while beta tin goes only to 150. And so then if you compute this free energy, right, the just magnum free, phonon free energy as a function of temperature, then basically you can occupy these phonons with a lower bandwidth much more efficiently, right? And so that means that after some temperature, this beta phase that's higher in energy originally gets lower in free energy at the temperature slightly above 300 Kelvin. And so here, basically, you see the calculation of the free energy for these two phases. So beta phase is initially higher free energy because it's high energy. But then due to the entropic terms, due to having narrower phonon dispersion, phonon bandwidths, it gets stabilized. And basically, this phonon free energy is what can help us also to deal with these dimers. So, in this system, like Fermi surfaces are quite complicated, and the phonon dispersion is also. But here I tried to plot the phonon dose for the limiting cases. So the first limiting case is high temperature state, right, where there are no dimers. And I have this violet curve. Now, in the dimerized phases, I'm looking at the state with the highest possible, like lowest temperature and lowest possible concentrations of dimers. So these are my two, wildest states, and all the dimerized states are between the two. And so what I see, in addition to this phonon spectrum, that runs to approximately 5 terahertz for undimerized system, right? I get these high energy phonons around 6 terahertz. And so the spectral weight is transferred from these lower frequencies, right? The phonons are created at much higher frequency. And these are the phonons localized on these rigid bonds. So essentially, I'm getting this situation where the dimerized states, they have lower energy due to the bonding, but they have harder phonons. So they cannot gain so much on the entropic term of the free energy. So, well, we weren't able to do some high throughput calculations to maybe, compute the phonon density of states for all kinds of different materials. So we tried to do something kind of rough, just subtracting the phonon density of states of Q5 minus HT and Q6 minus HT, right? So trying to estimate what is the modification of phonon density of states per dimer in these two states. And actually, they look remarkably similar, despite the states are quite different, right? So basically here I'm subtracting the 1/5 state minus high temperature phonon dose and 2/6 states. So this is the highest experimentally observed dimer concentration. This is the lowest. And these are basically contributions per dimer in these two states, in these two limiting states. And they are not too far away. Essentially, we see positive peaks close to 6 terahertz. So these phonons are moved to higher frequencies. And then there are some important modifications also at lower frequencies. But generally, the spectral weight is taken from lower frequencies and put in the higher frequency states. So then basically I can approximate the change of the phonon dose as the number of dimers times this function, right? Times some average between these two functions, and then plug that in the phonon entropy. And if I compare now the if I compare the free energies computed this way with the addition of the phonon entropy term, then I'm supposed, in principle, to get the the phase diagram. So one other ingredient is that the energy of the dimers themselves. And so I'm trying to estimate it from this earlier plot. Basically, here I see that the energy goes linearly with the number of dimers, approximately linearly, right? But then it rises very quickly. So this steep slope is not so easy to model with some reasonable polynomial. Like we have to actually go to quite high powers. But so for a simple model, it suffices to introduce a quadratic term that basically implicates that there is a minimum energy at a certain dimer concentration. And then the states with higher dimer concentration are disfavored energetically. So this is what we are doing. So I'm just introducing kind of negative chemical potential, right, minus mu n, and then this term takes care of disfavoring states with too high dimer concentration and the entropic term. And then if I just compute the energies for all these states that are basically obtained from this series identified experimentally, then I can basically equate the energies, and I get the dimer concentration as a function of temperature in some form of some infinite staircase. So of course, in a real system, there is a strong coupling to the lattice, so I will not have infinite number of states. That's kind of hopeless, but at least the general trend that the states are staying for longer temperature intervals, towards higher temperatures, and then the phases get narrower in temperature, that is preserved here. And in principle, this is a rather simple model that shows how to get, this many phases kind of using ab-initio inspired parameters. So for this part, I would like to conclude. So I have explained that modulated phases in iridium telluride are likely due to the competition of iridium-iridium bonding and entropy. There are much harder phonons on the dimers, which makes entropy contribution lower, right, and drives states with less dimers, with higher dimer concentration at lower temperatures. It's interactions, elastic long-range interactions through the lattice between the strains that dimers introduce that are basically determining the organization of dimers in the stripes. And due to strong coupling to the lattice, unlikely it will be possible to see this whole devil staircase, but still, I mean, one can explain this with such a simplified model, one can explain many phases. And ultimately, it would be interesting to try some fully automatic prediction of these phases, and that's something I have no ideas how to approach. Thank you very much.
Thank you so much.